As we dive deeper into our study of limits, let's now take a look at limits as we approach infinity. And I started with an example here. So here's my function, x plus 1 over 2x, and it's here in blue. And you'll notice that there's two asymptotes in this rational function, one where x is 0 and one where y is a half. So if we take a look at a limit, and we're going to look at two of them. We're going to look at what happens as x approaches negative infinity. So as it goes left and gets really, really small. Well, what happens to this particular function as it gets really, really small is it gets very close to 1/2. Looking at the other side as x approaches positive infinity. So as x gets really, really big in this function. So now I'm looking at this half of that function. It looks like it's approaching that same line of 1/2 the farther I go to the right. So to define this idea of a limit at infinity, we talk about a function, we talk about having a couple of limits being real numbers, and then we have these two definitions. The limit of f of x as x approaches negative infinity happens to approach one limit, and the limit of f of x as x approaches positive infinity happens to be a different. And they can be different, they don't have to be the same. We're just looking at one versus the other. This is how we note the limits at infinity. Now this bottom part becomes really, really important. So I threw a little star on that. This says the limit of 1 over x to some power r as x approaches infinity is 0. It doesn't matter if it's x squared, if it's x cubed, even if it's x to the first. If I have something like this, that limit is 0. On the other side of it, as I look at negative infinity, so as things go to the left, if I have this 1 over xr, as long as x to the r is defined. Okay, if it's an undefined situation, we have a whole other mess. But as long as this is defined, then that limit is also 0. So these are going to be the two key things we use. And here's how we use them. I did a couple of examples here. First example says the limit as x approaches infinity, and here's our function. Why this helps us out. I broke this into two separate parts, the limit of 4 and the limit of 3 over x squared. And what I did is I took them as separate limits. Now the limit at 4 is going to be easy. Okay, it's just going to kind of carry through, and it's going to end up being 4. If I get really, really big, if x gets really, really big, this just continues to be 4. But the other part, I'm going to take the 3 out of this limit, because 3 is going to be 3. But look at what happens with what's left. I'm looking at the limit as x approaches infinity of 1 over x squared. Now, by definition, this tells me it's going to be 0. But let's think about plugging in numbers. Let's do this numerically. If I plug in a 1, this is 1 over 1. If I plug in a 2, this is 1/4. If I plug in a 3, it's 1/8. We're looking at infinity. Think of 1,000 squared. 1 over 1,000 squared is a really small number. Think of 10,000 squared. Think of 1,000,000 squared. This number is so small that it's getting closer and closer to 0. And so by definition, the limit of 1 over x squared is 0. So I've got the limit of 4, the limit of 3, which is just 3, but that's being multiplied by 0, so 3 times 0 is 0. This has a limit of 4. Now, to get into the algebra side of this process, we're going to find the limit as x approaches infinity. What we're going to do is we're going to take the largest power that we can find, and we're going to divide everybody by that power. Now watch what happens when we do this. So I took everything in here and I divided it by x squared. So right here I've got an x over an x squared, so that leaves me with a 2 over x. That's going to go to 0 as x gets really big. Here I've got a 3 over x squared. Doesn't matter, there's a 3 on top. this x squared on the bottom is going to make this get very, very big. Here, this simplifies out to 3, and this is just a 1 over x squared. That's going to get really, really small as I plug in large values of x. So that's going to go to 0, that's going to go to 0, that's going to go to 0. I'm going to get 0 over 3, which is just 0. This thing's going to get closer and closer to 0 as x approaches positive infinity. Now, I fine-tuned it just a little bit. Now I put in an x squared in that top one. Now, overall in this function, if I look at all the small pieces, the biggest value is still x squared. That's the largest power that I see. So I divide each piece by x squared. And anything that has an x squared still on the bottom is going to go to 0. That's going to go to 0. But now I have a little simplifying to do. This particular function is going to get closer and closer to negative 2/3. My last one, now my largest value, my largest power that I see of x happens to be a cubed. So I'm going to divide everybody by x cubed. And I'm going to do the same process. Anybody who still has an x on the bottom is going to go to 0. This is going to have an x cubed on the bottom. It's going to get to 0 even faster. Now, simplifying here, yes, I'm going to cancel a couple of them, but 3 over x is still going to go to 0. This is the only one that doesn't have anything going on. The x cubes cancel, and I get negative 2. But I run into kind of a new problem. Negative 2 plus 0 I can do, but 0 plus 0, I can't have a 0 on the bottom. So as this particular function gets closer to infinity, I don't have an answer. I have an undefined situation here. I can't do this limit. It must be getting very, very big. It's approaching a big number. When we talk about infinite limits or limits at infinity, the other thing that naturally comes into discussion is the idea of limits of sequences. Again, I started with an example. Here's a sequence where I'm just doing 2 to the power. Now notice with these numbers, they are getting closer and closer to 0. So we can actually take the limit of this sequence, 1 over 2n, and as n approaches infinity, this limit is going to get closer to 0. And we're not talking about these smaller numbers. Think big numbers. Think 1,000, 10,000, million. If I take 2 to the millionth power and take 1 divided by that, I have a very small number that's essentially 0. Now, because the terms of this sequence are getting closer to 0, or a number, we say that they converge. And we've used this language when we've studied sequences in the past. Of course, a sequence that does not converge to a specific number is said to diverge. So if it approaches a really big number, if it approaches a really small number like infinity, we cannot find that limit. We say it diverges. Think of an arithmetic sequence, or think of a geometric sequence that gets bigger. We're never going to approach some specific number. So I put some examples up here. The nice thing about these examples is we handle the same way we handled limits at infinity. If we're looking at what happens to this sequence as n approaches infinity, we're going to divide by the largest power we see. So in this first example, the largest power I see is n to the first. So I'm going to divide everybody by n to the first. Anything that still has an n on the bottom, here's 1 over n, that's 0. Here's 4 over n, that's going to approach 0. But anything I can simplify is going to help me find the limit of this sequence as n approaches infinity. Here I'm going to divide by n squared, because that's the largest power I see. And again, anything that has an n on the bottom, this has an n squared, it's going to go to 0. This has an n squared, it's going to go to 0. Even simplified, this becomes 2 over n, it's going to go to 0. This is the only one I can actually simplify a little bit, and I get 1, but 0 over 1 is still 0. So this particular sequence is going to get closer and closer to 0. Again, largest power I see is n squared. You'll notice that there's 1 on top and 1 on the bottom. Up here there wasn't. That's going to change things a little, but it doesn't change our process. I'm going to divide everybody by n squared. Again, anything that has an n or an n squared or some power of n on the bottom is going to go to 0. But if I can simplify, this is 1/2, so that means this sequence, as I plug in bigger and bigger numbers, this sequence is going to get closer and closer to 1/2. I could still do this graphically, I could still do this numerically, but this particular sequence, as the numbers get bigger, I'm going to get closer and closer to 1/2 for my answer. Let's take a look at what happens when the top has a bigger power. So here I'm going to divide by n cubed. 2n cubed over n cubed, 1 over n cubed, n squared over n cubed, 1 over n cubed. And again, anything that's going to end up with an n on the bottom, some power of n on the bottom, is going to go to 0. Anything I can simplify, I simplify. This one doesn't have a limit. I can't divide by 0. There must be something else going on. When I start plugging in bigger numbers, this thing must be taking off, increasing without bound, getting closer to infinity. The bigger the number I put in, the farther this takes off. I can't find this limit. It doesn't have one. It's not approaching something. It's just changing continuously. I put this last one in here. It looks really complicated, but it leads us into what we're going to talk about when we get into the area problem. But I've got a sequence. It's complicated. Let's do some algebra here. Got a little work inside this parenthesis. I've got some foiling to do here, and when I'm done foiling, I've got an n to multiply in. So when I put these two together, I get a 2n squared plus a 3n plus a 1. And I've got this n to put in, so these powers are all going to go up by 1. And then I have this 8 over n cubed to put in. So I'm going to go ahead and put that in. So I get 16n cubed, 24n squared, and an 8n. And on the bottom I have a 6n cubed. We're going to attack this problem just like all the other ones. We're going to look for the biggest power of n, which happens to be n cubed. It's here and here. It's the biggest power I see. We're going to divide everybody by n cubed. When I divide this by n cubed, it's going to go away. When I divide this by n cubed, it's also going to go away. These are the only two I really care about. When I divide them by n cubed, I get a 16 and I get a 6. I should probably reduce that. They both are divisible by 2, so I get an answer of 8/3. So this particular sequence, if I start plugging in bigger and bigger and bigger numbers for n, here's the simplified version, this is going to get closer and closer to 8/3.